Hello everyone. In this video, we will continue to examine high-mass stellar evolution. So recall that the final stage of fusion for this star is the fusion of iron from silicon, and that happens in the space of a single day. What happens after that is simply astonishing and is one of the most powerful and radical events in the universe. So when fusion finally ceases, due to iron buildup in the core, the outward radiation pressure from the fusion drops like a stone. It drops almost instantaneously in the space of a second. The core collapses incredibly rapidly from about 10,000 kilometers wide to nuclear density, and the temperature skyrockets to about 10 to the 10 Kelvin. This is 1,000 to 100,000 times hotter than it had been just zero point 0.1 seconds before. This incredibly high temperature core material releases gamma rays in a fraction of a second. And those gamma rays, that incredible flood of gamma rays, completely split apart virtually all of the iron that the star had worked for millions and millions of years to produce in a single second. This process is known as photodisintegration, and all of the iron virtually is now helium. So those gamma rays completely blow apart the core, which is important to recognize absorbs energy. So this is an absorptive process and therefore further reduces the radiation pressure. The collapse of the core then continues, overwhelming the electron degeneracy pressure. So the core collapse has enough gravitational pressure to completely blow through the pressure produced by the Pauli exclusion principle and forces all of the electrons into the protons at the center of the nuclei, giving this reaction here as an electron and a proton combined to become a neutron and an electron antineutrino, until the core reaches nuclear density with a core mass greater than 1.4 solar masses. Recall that if it were less than 1.4 solar masses, that core would stay as a white dwarf. So this core collapse continues until that core reaches nuclear density. When nuclear density is reached, though, you then run into neutron degeneracy pressure. So not only is there electron degeneracy pressure, where electrons are sort of pushed outwards due to the Pauli exclusion principle, neutrons are also fermions, if you remember, and they have their own associated degeneracy pressure, which is much higher than electron degeneracy pressure. This is the pressure that can be associated with the neutrons literally not being forced into one another. So it is the pressure that keeps the nucleons in the nucleus from literally merging. And that neutron degeneracy pressure kicks in a fraction of a second. The core becomes incredibly stiff all at once. And all of that inrushing material from the outer layers of the core bounce off that inner neutron degeneracy pressure slash neutron density level core. This bounce progresses outwards in an explosion that we know as a supernova. This is a massively, massively luminous explosion, roughly 10 to the 46 joules of gravitational potential energy, which is the original source of this energy. Remember, all that mass has just fallen. So that's gravitational potential energy, not nuclear energy, is released. This is roughly 100 times the lifetime output of our sun in a fraction of a second, and it blows the star apart. The intense gamma ray radiation and energy leads to the synthesis of elements with mass number higher than iron. And this is the only source in the universe, other than artificial sources, of those elements. So all of the iron and uranium, sorry, all of the gold and uranium and anything at all on the Earth with a larger mass number than iron is produced or was produced in a supernova. Um, these explosions have the luminosity of galaxies. And so supernova are just incredibly powerful phenomena. Um, as a result, we can see them, and it's really extraordinary to catch them. It's one of my favorite topics, in part because this is what I wrote my thesis on. So supernova become approximately galactic level brightness for months, from anywhere to from about a month to 2 months. And the core collapse supernova we're talking about right now, are shown in this diagram here, and you can see that they reach a maximum luminosity, you know, uh, just a few days after explosion, and then slowly tail off. Um, and in this picture right here, this quite beautiful, vivid picture, you can see that the supernova that is captured in this picture is approximately the luminosity, or is in the same ballpark as the luminosity of the entire galaxy that it's in. Uh, Remember, there are 100 billion stars in this picture right here. And you can see that luminosity sort of get brighter and brighter and brighter and then dimmer over the course of months in these images here. It starts out um, right here. Notice that it is the same brightness, give or take, as this star right here, but this star is in our galaxy and nearby. This dot right here, that star, that supernova, is in another galaxy far away. And you can see it get brighter and brighter and brighter and brighter, and then start to fade over time. Notice this is in October, and by the time this sequence of images is done, this is in January, mid-January.